Hello everyone, and welcome to the second half of this introductory materials informatics course. So in the first part, Professor Krishanu Viswas has been talking about the different types of machine learning algorithm and how you actually do the machine learning and so on. Now, doing proper machine learning is also contingent on having a good set of data with which you can work with. And how do you actually get the data? From where do you get the data? How do you structure the data? All of those things we will be covering in the second half of the course. So after we talk a little bit about the data itself, we will move on further and we will start talking about the microstructure informatics and different principles of featureization. How do we do high throughput generation of data which you can use in order to build your machine learning models. So all of those things we are going to cover in this second set of 20 lectures. So what we are going to do today, initially, we'll just go through a little bit of history. We'll look at how different inventions and discoveries have been made. Let us study the process of inventions and discovery, because at the end of the day, what we are doing is we are trying to use machine learning techniques in order to accelerate the discovery of materials. So if we look at the initial discoveries that were made, we are all familiar with Thomas Alva Edison, and so the first method that we want to talk about is the Edisonian method, which is that of trial and error. And Edison, when he was designing his light bulb, he had at least 3,000 trials, and he ended up making lots of bulbs which worked for very few hours until he eventually came to the one which kept on working for an extended time frame. So you know that later on we all moved towards this tungsten filament type of bulb. This is something that Edison also thought about earlier, but this is something that he was not able to try out simply because he didn't have the right set of tools. So one of the things we pick up from here is, as we go about collecting data, it's important not only to know what we want, but also it's important to know how we are going to get there. So in that sense, knowing the set of tools is going to be extremely important in order to generate the right type of data. So after so many trials, eventually Edison settled down on using carbonized filaments. And as he was searching for this potential filament materials, he ended up looking at a total of 6,000 different fibers. So that's a lot of trials that Edison had to do. And any invention or discovery that you make by a process like this is quite time intensive, and it is definitely quite expensive. And after going through such a laborious process, such an exhaustive process, Edison came up with his very famous quotation that a lot of people use today, that genius is 1% inspiration and 99% perspiration. So moving on from Edison, it's important to know that it's important to recognize that Thomas Edison is actually a rarity. It is very rare that somebody does that many large number of trials with so much of dedication. Most of the discoveries that came about in the 21st century, they came about through a process of serendipity. Many times people actually started out to find something else and eventually ended up with a new discovery that they were not expecting. So they ended up finding things by chance. So this is basically what we call serendipity. So talking about such accidental discoveries, there's many of them, but we'll just touch upon a couple of them. The first one is that when Leo Baekeland was actually setting out to come up with some sort of an alternative for shellac, it's a tree-based resin that you get. And so he started out by making some sort of a mixture of formaldehyde and alcohol, which is basically a phenol. And the goal, of course, was to make shellac. But what happened was, he accidentally ended up making bakelite, which is one of the most widely used materials that we have today. If you look at the discovery of a lot of other polymers such as nylon or Teflon, all of them were also accidental discoveries where the inventors had actually set out to make something else, but then they ended up making those type of new polymers. Moving closer to the metallurgical engineering domain, Harry Brearley was working on materials for gun barrels. And he was actually trying to make materials which were very much wear resistant. And he tried lots of different steels in the process. And one of those steels was something which had a lot of chromium. So initially, Brearley was not that thrilled about this high chromium steel, and he threw it away in his wastebasket. And then many days later, when he was clearing out the basket, he saw that there was only one piece of metal that was shiny, and that was the high chromium steel. And so the search for gun barrels and wear-resistant materials led to the accidental discovery of stainless steel. So there are many such discoveries in history, but then these are all accidental. Now, if you look at this sequence of discoveries, we had people who worked really hard in order to make these discoveries. We had people who were looking at other problems and ended up making accidental discoveries. What do we actually learn from them? Can we make the process of discovering new things a little bit better? So this is where it became important to ask the right type of question. So I'm just going to touch upon very briefly upon the discovery of metallic glasses by Paul Dewey in Caltech. So Dewey asked a very interesting question. So he asked, what happens if metallic liquids are allowed to solidify without nucleating? So now those of you who are a little bit familiar with the process of solidification, you would know that solidification starts with nucleation, where a small nuclei, which is nothing but a cluster of atoms, which comes together and forms inside the liquid, and it is this nuclei which eventually grows. You will have lots of such nuclei forming in the liquids. They all glow together until they impinge upon each other, and that gives you the microstructure of the material. So Dewey's question was, it's very interesting, that what happens if we don't allow the nucleation process to happen? And so that was a very pointed question. And how do you actually go about doing it? So first thing he realized is he would have to take a very suitable system. So he went with this gold silicon alloy system, which forms a very deep eutectic. So what was the need for the deep eutectic? You want to keep the liquid a liquid. You don't want to let it to solidify. And therefore, what he did was he took a eutectic system where the melting points are lowered, meaning that the stability of the liquid at that particular eutectic composition is automatically high. So he took a system like that, and he rapidly quenched from the eutectic, this eutectic mixture from the liquid state using a technique known as melt spinning. So essentially what happens is, here you inject the molten liquid onto a copper disc which is spinning very fast. Why copper? Simply because it has excellent thermal conductivity. It's going to conduct the heat away very fast. It's going to cool the liquid very fast, and as a result, you end up freezing the liquid without really giving enough time for anything to nucleate in that. So when Dewey went through this process, he discovered something known as metallic glass. And then coming much closer to the modern times, I want to talk about one final discovery before we move into the machine learning driven discoveries of materials. So here I want to talk about the discovery of quasicrystals that was made by Professor Dan Shechtman. So now those of you who are have a little bit familiarity with crystallography, you will know that in case of crystallography, we have 2-fold, 3-fold, 4-fold or 6-fold symmetries, but 5-fold symmetry or multiples of 5, those are what we call forbidden symmetry. Classical crystallography would tell you such crystals will not exist. However, Professor Shechtman actually discovered a 10-fold symmetry by doing TM diffraction on a very rapidly solidified material. And so once he saw that geometry, he could not actually believe his eyes, and his reaction was "En kaya kazo," which basically means such a beast cannot exist in his native language. Now, what was the consequence of that? This literally changed the very definition of what a crystal is. People had a very hard time believing that this was anything beyond experimental error, and he was disowned by his own group and his group leader. And Shechtman was opposed by none other than somebody like Linus Pauling, someone who had already won 2 Nobel laureates. But this is a story of courage. Shechtman had the courage and conviction in his understanding of the fundamentals of the technique of TM. He held on to his idea, and eventually people understood that there is a new class of crystals which we call quasicrystals, and as a result of that, the International Union of Crystallography, they ended up changing the very definition of crystal. So this is where you have a serendipitous discovery, but then you rely on a very strong set of fundamentals and courage in order to identify the discovery properly and then move forward. So far we have been talking about discoveries which were made by huge amount of hard work through the Edisonian method of trial and error. We have talked about accidental discoveries, the discovery of bakelite and the discovery of stainless steel. We have talked about discoveries which come about as the result of trying to answer a very pointed and a very well thought out system. And then we have talked about discovery which require a lot of courage, which could be accidental, but they rely on a very fundamental understanding of the technique by the inventor. So whether these discoveries are intentional or serendipitous, most of these discoveries, they also face stiff opposition when they're initially reported. Now, if you think about how these materials are designed and then translated to service, once you make a material inside a lab, that is done at a very small scale. You need to try and scale it up. And therefore, before you even get to the scale up process, you actually need to ensure that the material is really that good, at least it's as good as what you are claiming. And so that is where the process of code validation comes in. And code validation requires extensive amount of testing. So once materials are code validated, they can be then increased to the level of pilot plants and so on, and then slowly they get translated. So just to give you an idea, if you think in terms of materials for, let's say, a jet engine, typically it will take you 20-30 years for the material to go from the lab to the industry. So the bottom line is, whether intentional or serendipitous, most scientific discoveries will require a lot of hard work. And one thing is also certain, that whenever you come up with something new, it faces a lot of stiff opposition from your peers. So if you take the typical timeline of a material being designed in the lab and then getting translated to applications like that of a jet engine, the time frame that elapses is quite large. It could even be 20 years quite easily. And so basically what happens is, once you make a material which you are really excited about in the lab, you need to do huge amount of testing. You have to make samples that conform to specific dimensions and so on, and those samples get subjected to long-term tests. So this is basically what we call code validation. There are lots of ASME type of codes, and you have to code validate a material before it can be taken up forward in let's say a pilot plant and so on. And then after it's used in a pilot plant for a long time, you might actually be able to sell it to the industry and basically make the jump from the lab scale research to the actual application. So one of the questions that we've got to ask ourselves is, by using machine learning, is there a way in which we can even accelerate this process? So this idea of using machine learning for materials discovery and design is relatively recent. This came about only in the 21st century. And if you look at the early stages, two gentlemen, Pierre Villars and Z.K. Liu, they were actually bouncing off ideas of each other that can we do something which is similar to bioinformatics, and then come up with a system of materials informatics. And their initial discussions and their initial efforts led to what we know as the Material Genome Initiative. So in addition to Pierre Villars and Z.K. Liu, Jebran Seder also played a huge role during the inception of the Materials Genome Initiative. And so if you look at what this Material Genome Initiative seeks to do, they are looking to facilitate the discovery of materials, and they want to do it through proper property optimization, further development of the material. How do you actually integrate the material with the given system design? Then there is certification or the code validation, which is what I was talking about. And then after that, you come to your manufacturing stage. So all of these things would be required for deploying a particular material. And then the idea was, with something like this Materials Genome Initiative, where you use a framework similar to bioinformatics, can you actually end up speeding up this process? So this was really what they set out to do. And this is, as far as I know, this is really where the genesis of materials informatics started. If we look into the scientific publications, the first sort of, I would say, successful story in applying machine learning to materials came by a series of researchers from lots of different fields. So we had people who came from a computer science background, we had people who came from a chemistry background, and they all came in together, pooled their respective expertise in order to solve a problem of designing a battery. Now, the idea was very simple. Design of batteries was not something that was new, at least from an experimental standpoint. And therefore, what happened was they looked into lots of experiments that were failed, both from the literature and as well as from their own lab. And using the data collected from those failed experiments, they came up with a machine learning model in order to predict the material compositions and conditions under which you could make a nice battery. And so this was the first one of the first, I shouldn't say, so this is one of the first works on materials informatics that really resulted in something quite novel. So as we look into materials informatics, we need to be cognizant of a few subtleties. So if you look at your traditional machine learning, people come up with a very huge data set. You have large number of data points, and once you have a large data set, you can actually do the fitting quite accurately. However, materials informatics is a slightly different problem. So here, materials are essentially a sparse data problem. The volume of data that you have got is relatively less, and so that means the approach is going to be a little different. So you cannot arbitrarily select features. You have to select the features very, very carefully. And when you try to select the features very carefully, you have to essentially know the field of material science quite well. So that is the first part. The second part, especially when you are working with sparse data, is you really want your models to be interpretable. You want a situation where you can make predictions, you can test them experimentally, and you can really understand, you can unravel this black box nature of the machine learning process. And again, that requires a good understanding for your basic material science. So if you look at a lot of the traditional machine learning problems, they deal with lots of averages. They want to look at what is the average interest of a set of consumers and so on. As a material scientist though, we try to deal with extremes. We want to find the best possible composition, the best possible processing condition, and so on. So this is another way in which our materials informatics might have to differ slightly with your traditional. Having considered all of these subtleties, there's a few things which we should recognize as being extremely important. And the take-home message that I would like you to take with you is that the role of domain expertise is extremely important, because materials informatics problems in most cases turn out to be sparse data problem. So over here, what you can see in this plot on the left hand side is how much different featureization schemes results in an improvement in the predictions as a function of the number of training data. So if you get a chance, I have put the reference for this paper right at the bottom of the slide. I would want you to go ahead and read through this paper. It's a really good read. And so basically what the authors have done over here, they have looked at different types of featureization scheme, and the fractional is kind of a randomized featureization scheme where you don't really take the domain expertise into account. And then others are just different ways of featureizing where different aspects of materials has been considered for making predictions. And what you see, the really important part over here is that as the number of training data is small, so somewhere of the order of hundreds, that is really where how you featureize the problem, how you featureize the machine learning problem, that really plays a big impact. And so for sparse data problems, the role of domain expertise is quite immense, and this is something that one should not ignore. So when you are going for a materials informatics problem, please keep in mind you need to know not just the machine learning aspects, but you need to have a good idea of the domain as well. Or if not, you should be working with a domain expert who can guide you in terms of which of the features make sense and which do not. Now, the other thing to keep in mind is when you are looking at the choice of the different machine learning models, you will always have a trade-off between the accuracy of the model and the explainability of the model. it turns out that when you go for much more complicated models like an ANN model, for instance, it becomes really difficult to explain how the model is behaving, how the decision making process is evolving, although you will be getting some rather accurate results. On the other side of the spectrum is much simpler models like linear regression and logistic regression. So these are fairly easy models, and these are the ones which you can really explain the predictions. You can really make sense of why these algorithms are predicting in the way that they are doing, but the accuracy is relatively going to be less than something like a artificial neural network and so on. So these are just a few things which you should keep in your mind as you start in your materials informatics adventure. So with this, we will slowly start transitioning into different materials data repositories. If you look at the data repositories, this is not a new phenomena. People have been building databases for a long time. But the earlier databases did not have an API, and therefore accessing those databases was a bit of a challenge. You could always look up the data you needed, but if you wanted to import data in bulk, that was difficult. So just a few of the earlier databases I have listed over here. So you've got the energy materials data mining, which is hosted in UCSB. That's an excellent database if you're looking at energy materials. People have dedicated databases for topological materials in this topological quantum chemistry website. And then, of course, you have got a lot of data in traditional materials journals. And nowadays, you even have this data in brief type of series from where you can get lots of data. One of the challenges you might face is a lot of this data would be present in the form of plots. And so here you can start using tools like the webplot digitizer and so on if you want to extract numeric data from those plots. So all of this thing becomes important when you are looking at the slightly older databases which do not have an API. Nowadays, a lot of these modern databases, they are API enabled. So you can actually do a little bit of application interface programming, and you can pull in the data that you want based on certain filters that you create. How do we do it? We will look at it in the next lecture. But I'm just going to list out a few examples of the relatively newer databases which are API enabled and have good accessibility from within the materials informatics code that you are putting together. So one of them is the ChemSpider, especially if you are looking at things which are more chemistry related, more of the chemical aspects of materials. Then you have got a wonderful database called AFlow, which stands for Automatic Flow for Materials Discovery, which is maintained by Professor Stefano Curtarolo. And then you have got the OQMD, which is the Open Quantum Materials Database. And this is something which is maintained by Chris Fullerton. Of course, one of the earliest of this new generation materials databases is the Materials Project, which is maintained jointly by Gerben Cedar and Kristen Persons. And this happens to be also an excellent database that one can look into. And finally, another one worth mentioning is the Computational Materials Repository database. So as we move forward, what we are now going to do is we will take a look at how these databases are structured, what really should be there in the database, and then after that we will go through a number of online data repositories, and I'll just give a brief commentary on the relative strengths that these different data repositories have, and if there's any sort of API